Right. Ladies and gentlemen,
This is such exciting stuff.
right. Yeah, I can hear that. Right. So, a couple of you. Well, firstly, my apologies. Apparently, the Dennis marked much faster than I do, so Mr. Wood joined me in the evening at 7 last night. You scheduled first for the next project. I think it went well. I had the impression that the class average would be around about 80 for the project. So I think 1 or 2 people are unhappy. Everybody who did email me, I'm looking at all those cases personally to see whether sometimes you have a disagreement with the demi. Somebody was very unhappy about the way I allocated marks in the parking schedule. Things, that's what it was, and the whole rest of the class did that. So, but I think all in all it went well. There was 1 person who had some trouble with the Git repositories. So please don't delete from your repository. To get a nice clean submission, make 1 directory which will be your final submission directory. And if you want to push other stuff as you go along with project 2, do so, but then at the final directory, which is clearly the final submission directory. For the next project. 1 or 2 cases of Mr. Weissman. Here. 1 or 2 cases, yeah, sorry. I saw that Josh emailed me that your and then I emailed you at 5 this morning till he was not in, but actually remember it must also was the deadline. I think it was 100. I think it's really good. So I did not get the impression that all in all the class is about to throw me with rocks because of the project demo. So if there are general things that you're not happy about, please ask Lucia, and she can make a list if it's the case. Otherwise, I think things went well. But that being said, there's a difference between unit tests and coverage. I know that some of the demis marked you very generously, giving you 10 out of 10. If your coverage was okay, even if your unit tests were terrible. So please look at that. Make sure you get that right for the next project, because the next project we're going to mark that very strictly. Okay. It's a useful tool. Use it. Not to get marks, but because it's a useful tool. Okay. All right. Any more questions? I have already had a question about 4. You want to have a look at test files for project, well, specifically for Tab 4. You can look at the book size, because we are starting with graphs this morning. Nice schedule. Just when you start with project 2, I start with graphs. Okay? And there are a lot of examples of graphs on the book side. So you can use that already to test your, just your layout. Remember, you have to draw nodes and then you have edges connecting them and so on. Okay? Right, so let's do this. Be ready on Friday for your graphs. Okay, what do I mean by a graph? Not an XY graph doing this, like in maths and linear calculus. By graph, I mean that thing you already saw in your first year. A node represented by a circle with a name in it, and then a line nodes, which means there's an edge. So a graph, in the sense that we are using it from now onwards, unless otherwise specified, a graph is a set of vertices or nodes. Vertex is too long a word, so I say node. Node and a vertex is the same thing. And a collection of edges that connect the vertices. Now, why on earth would we want that? Well, think a little bit. The binary search tree is also a graph. We use graphs all over the show to do imaginings. It is the basic abstract data type that we use in this. A graph gives relationships. So if you look at your project 2 spec, you'll see an example of such relationships. But any two things that are related, for example, suppose I want to see where all the Wi-Fi hotspots are in Stellenbosch, and I want to see what the distance is between them, so that I can know if I move along from hotspot A to hotspot B. If I walk from here to my res or place of residence, or like flat, whatever, wherever you say, whether I'll lose my Wi-Fi signal. And so if two hotspots are connected in the sense that you won't lose the connection, then you can do a graph, you can do a picture. And many other such things. A couple of years, never mind, okay. You can, for example, also draw a graph of the internet. Where are the nodes? Where are the servers? If you want to look at the activity on World of Warcraft, okay, that one's getting but okay. You want to look at where the servers are for World of Warcraft versus where I am. I'm going to Japan for holidays. Where can I connect to which server and so on and so forth? You draw a graph. Okay. So we are going to use graphs, and as you progress, the applications just fall out naturally. Okay. So just a few conventions and notations. The edges is a set from a node to a node. So the nodes generally we abbreviate by small v and small w. So I can say there's an edge from node v to node w, and I draw it like, write it like this. So a graph itself is a pair VE, yes, because it's the set of vertices and the set of edges. When we start doing proofs, you get that. Okay, that's all. Please note this. If I have a line between two nodes, this means it's an undirected edge. Yeah. So if you are in a relationship with someone, A and B, you are A, the other one is B. then you being in a relation, A being in a relationship with B normally means B is also in a relationship with all sorts of things can happen in relationships. Let's not go there. Okay, but your relationship with your father is a directed relationship, not an undirected one. Yes? Because there's a difference between being a father and a child. So there's a relationship from your father to you which says my child. And there's a relationship from you to your father which says my parent. So that's directed because it has a different interpretation. We allow things we call self-loops, but in the examples in the book never have them. In the examples, just because it complicates the example, but it's allowed and all the code will work if there's a self. So if you are an introvert, you're in a relationship with yourself, and that's cool. Yeah, so that's self. Parallel edges, so if you are one of those people who be parallel, have many girlfriends or boyfriends, then there are parallel edges. Okay, so that's also allowed and the code will work for it, but we just don't show it in the examples, but it is allowed. Okay, right. Now when we look at graphs, we just have to get some more terminology right. If you show me a random graph, there are things that I can identify. One of the first things of interest is a cycle. So if I am currently here, I can follow a certain path and end up with myself. Again, same place where I started. That's a cycle, informal. There's a good definition in the book. And that is, of course, relevant for algorithms because you don't want to fall into a loop. This is a loop. And you want to make some algorithms won't work if you have a loop. So some of your graph algorithms will only work on acyclic graphs. Acyclic meaning there are no cycles in the graph. Then you have an idea of a connected component. This graph consists clearly of 3 different parts. And this little part here, none of the nodes in here have an edge to any of the other 2 big parts. Right? So these are components. Yes. And this little one in itself is a connected component, this one in itself and that one in itself, but the graph itself is not connected because it has 3 separate components that are not joined to each other. Does that make sense? A path is any order of nodes that I can walk through. So I can start there, go there, go there, go there, and then this node followed by that node, by that node, by that node is a path. Okay. We are going to differentiate between simple paths and simple cycles, just to keep the algorithms easy. But for the moment, assume that this will always be the case for a path or a cycle unless we say it's not the case, right? So a simple path is one with no repeated vertices. So I cannot, this is a path and this is a simple path. A goes to B, goes to C, goes to D. But A goes to B, goes to C, goes to D, goes to E. Contains a cycle, therefore. So in general, when we talk about paths, we keep things as simple as possible. What we do is we're going to develop algorithms, and then we assume it works on simple paths, simple cycle, and so on. A simple cycle is then a cycle that doesn't contain cycles in itself. It's not nested, it's in for loop. Cycle is a single for loop. A simple cycle is a single for loop. Non-simple cycle is nested loops, and so on. Okay, let's just formalize. No, wait. Just one thing that you have to note when we talk about a path. Remember, a path is a set of vertices, but the length of the path is the number of edges, not the number of vertices. Because that's how far you walk. I'm in town A, I'm in town B, in town C, and I walk from A to B to C, but my length is the length of this edge plus the length of that edge. A graph is connected formally. If there is a path from every vertex to every other vertex in the graph. So over here, for example, thingy is connected because you can do this at home if you or take colored pencils and start with every vertex and see whether you can get to all the others. And indeed you can. So if you connect it, if you have a connected graph, and now you can see the algorithms jumping out. If I have a connected graph, it means I can start at any vertex and get to any other vertex. There's nothing drifting, floating in a space bubble. It's all connected. Okay? Right. And now you know graphs already, actually, because we've worked extensively with trees up to now. We did a BC, red, black tree, we talked about 2, 3 trees, so you know all about trees. A tree then, if you want to look at it in graph terminology, is an acyclic connected graph. Why would that be the case? Well, think of the tree. We're drawing the tree right on the board. But what we keep on doing is we keep on doing this. And if I were to give you a picture of what I claim is a 2-3 tree, and then I join this thing there, it just doesn't make sense. Yes. So I cannot have cycles in a tree. A tree, by definition, is these things going down. So there are no cycles, therefore it's acyclic. And also it is connected in a tree. We never had something like this, sort of this little drifting branch on its own. We always connected everything to everything. If we have a single tree, then that is a tree. If I draw more than one tree, then this is a forest of trees. Okay. So unconnected trees in a certain sense makes a forest. And then we get this idea. Now you have to get your head around this. A spanning tree of a connected graph is a subgraph that contains all of the graph's vertices and is a single tree. What does that mean? And why do we want it? We want it because when we work with graphs, we are going to want to find the minimum length path through a graph. Yeah, you're a sales rep for Pep Stores because you failed CS214. So now, yay! some humor in class. And now you want to minimize your petrol costs because seriously you're not getting a good salary because you're a sales rep for petrol. So then you put the dots on all the petrol that you have to visit. And you can try to find the minimum length path that you have to drive this week so that you can set petrol. Therefore, what do we have? We have a graph. Yes. And if there can be a cycle, there should be a cycle, otherwise you won't ever come back home, which would be so sad. So there will be cycles in the graph. Okay? But what we want to plot on this graph is we want to connect all the vertices. Yes, we want to connect all the vertices in such a way that our connections form a tree. So here is an example of a graph. They don't, do they have cycles? Actually they don't, but okay. And over here is a spanning tree of the graph. What does that mean? All the vertices are connected in that tree. Yes, so the nodes in the tree are initialized with all the vertices, and then I decide how to fill in edges so that I get the tree, not a graph. So I want to cover all the vertices, but some of the edges will be superfluous. Has to be, because I start out with the graph and what I want to superimpose on the nodes is the tree. And we use that extensively when we want to find minimum length paths. And minimum length paths are all over the sheet. Round about when you were 10, 11, that is right. And then there was this big thing at the Varshaviks, that there was also so-called RoboCup. Are you familiar with RoboCup? RoboCup is so cool. They build robots that play soccer. And there was even the RoboCup team from Stellenbosch University. And that is fascinating, the programming, because you want to find the minimum length path to the goal so that you can score a goal, but you have to take into account all the what do you call it? Obstacles in between, who are the other teams players. And then when you get to image vision in your third year, if you want to do that, how does a robot see? How quickly can you see? How quickly can you work on the algorithms? Okay. So that was a big thing. And finding the minimum length path was up there. Okay. Right. Here are two examples of one thing that will be very important in all the algorithms. Seeing that we are doing an analysis of algorithm scores is how much space does it use and how quickly can my algorithm execute. Okay. Now, we will identify two different types of graphs, a sparse graph and a dense graph. The sparse, let's see, sparse. Julle kry dit, daarom staan die woordjie daar in, so that helps. The sparse graph means that if I look at the number of nodes and I look at the number of edges, they are comparable. Yeah, so I have a graph with 10 nodes and 20 edges. That's it's sparse. However, if I have a graph that is dense, that means there are many more edges than nodes. And then, when we get to the efficiency of the representation of a graph, you will see that the space and our major algorithm will be either in terms of E, the number of edges, or V, the number of nodes, or a combination of them. Right? So what we want to do would be for a specific implementation, a specific application, you might prefer one implementation over another. Because you can say, look, I don't have to store the edges, I only need to store the nodes. No, that's impossible. It depends on how I store the edges or the nodes. Right. Okay. So let us consider what we would want to do with a graph. Well, classic API, I want to know what the number of vertices and edges. I have an initial graph and I want to add an edge. Nodes are there. Nodes are always there. Well, it's because they form the graph. But then for a specific case, if I put graph G1 and G2 next to each other, and they have the same number of nodes, they might differ in the edges, how they are connected. So the edges form the structure of the graph. Okay? So we want to add an edge. But then, suppose, no, not suppose, for every single algorithm that we are going to do on graphs, you can imagine that I am at a certain node, and now I would have to follow the edges from that node to get to another node. For example, I want to build a spanning tree, or I'm searching to see if I am at node 1, is there a path to node 10? Well, the way to do that is to go to node 1 and see which edges do I have, and then follow the first one, blah, 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 recursively, and see, no, that's not connected to 10. Then I bubble back, and then I take the next one, and I do the same. So the only way you can actually process graphs algorithmically is this thing, to identify the vertices adjacent to a given vertex. Adjacency means if W is adjacent to V, that means there's an edge from V to W. Right. So let's look at the picture. 0 is adjacent to 6, 2, 1, and 5 because they're connected. 6 is adjacent to 0 and to 4. Yeah? And there's long sum. Yeah, they're adjacent to. Alright, so that will be the two things we want to have in a graph, any graph algorithm. Firstly, how do I build the graph? I add an edge. And then secondly, if I am at a vertex, how do I go to the next one? And I can only go to another one if I'm connected. Okay, so that idea of adjacency will be very important. Another concept that you have to know of is the so-called degree of a vertex. The degree of a vertex is the number of links leading that vertex. Yes. So in this case, for example, the degree of 7 is 1. There's one edge leaving it. The degree of 9 is 1, 2, 3. The number of edges leaving. Or if you want to put it differently, the number of nodes adjacent to it. Yeah, same thing. Okay. Sometimes it will be important to know the maximum degree of a certain vertex, or the average degrees, and so on. Okay. Now, so let's start right at the bottom because that's our favorite thing. How do I do it in Java? And how do I do it in Java? I can make the thing so slow that it doesn't scale. Not many of you, but too many of you had project once that did not scale. I guess about 5% of the class couldn't scale. But what worried me most, that was the people that demoed with me, where they didn't scale, they didn't know why they didn't scale. So you have to be very careful. I can tell you now, in project 2, if you don't scale, you're dead. Okay? Where scaling not means, look, I declared my array 100 instead of 500, but 500. Things were just so slow. I could go and get coffee and then Pixel didn't finish. 10,000 things. If you were one of those people where your Java code didn't scale, find out why. Because it's absolutely essential that you can scale. And the same will hold for project 2. 10,000 is not a lot. Suppose you go work for MTN over the holidays and they say, please sort my customer database. My word. If 10,000 takes you 10 minutes, that is just insane. Calculate what? 20 million minutes? One of the people who didn't scale fine. So that scaling has to do with either the bottom level implementation, right? So the direct Java, what did I use to implement my graph abstract data type? Was it an array? Was it a linked list? What was it? So it's all it is in the process of extensions of classes or whatever. But find out why. Okay. You do not want egg on your face in your first job because they give you this little thingy to do and then it's so slow that the company can't do it. So sort out how to do things quickly in Java. Okay. So let us think. In my low level implementation of the abstract data type, I have to know what the and I have to store the edges. Now here's one thing that we can use. Why don't I make a matrix of size b squared? Now and what I'm going to do is I'm going to say, you know what? I'm simply going to use Booleans. So if there is a link between 0 and 1, I'm going to put a Boolean there. But it's 1 bit. But then you'll have to force Java to physically just store 1 bit. So actually, I'm not going to use b squared integers, I'm going to use b squared bits, which is, depending on your machine and your compiler, 64 times less than, yeah. It's 1 versus 64 bits. So actually, that b squared is not as big as it seems. Now, where would this be a good thing? Well, if I have only a few nodes and a lot of edges, then to store each edge takes 1 bit. So the fact that I have an n squared array doesn't really matter that much because b is small. and each of the edges only take one bit. So that works well for dense graphs, because I only have really, it's only dependent on the number of nodes, not the number of edges. And now you can see, suppose I want to know to add an edge. Remember, we have the two basic operations. To add an edge would mean that I go to, from I to j, I would go to position ij and put a 1 there. If I want to know what is connected to 1, I have to read this line, this row, to see where I have 1s. Yeah, so that's easy and quick. Okay. That was this thing is called an adjacency matrix. It's a matrix and it shows which nodes are adjacent to the others. But this will only work with dense graphs, so in general, on average, one does not have dense graphs. It's very specific applications where you get dense graphs. Mostly we use this work with sparse graphs. Think of network connections and think whether that would be mapping the internet or mapping the physical lines for telecom, what is connected to what. Think whether that would be dense or sparse. Okay, right. So the other thing we can do is I can simply have a list of edges. What do I mean by simply a list of edges? I simply store pairs, BW. So I store, so my space, if I have a sparse graph, is clearly in order of E, the number of edges. But it's, so to add the edge is immediate. But if I want to know which nodes are adjacent to a current one, well then I would have to find this node and then I have to look through all the edges. So that's not a very nice way of finding all the nodes adjacent to the current one. So the standard implementation is what we call an adjacency list. So the adjacency list is an array of linked lists. And the index into the array represents the node name. And then it gives all the nodes that are adjacent to the current node. Yes. So this memory size that we need here is in order of V. Yeah, we store an array for every single node, but then for every single node, we want to know which nodes are adjacent to this. And the book uses a bag. You remember bags from test 1? No, you don't, because the moment you finish a test, it's all out. The difference between a bag and a set is that in a bag I may have multiple objects. Yes. And also, so I could have 6, 6 to 1 5. And what we have in this bag is unordered. There's no order in the bag. Although it looks in the picture as if there is an order, you will remember from a bag implementation that it is possible to iterate through a bag. So depending on the order in which one inserts edges into the bag, the order of these node names there might be different. And that changes your, not your algorithm, but just the order in which things happen in an algorithm. Things happen in an algorithm. Right? So this means, here are all my node names. Node 0 has a link going to node 6, a link going to 2, a link going to 1, and a link going to 5. So it is exactly this picture over here. 0 has a link going to 6, 1, 2, and 5. Okay? And the reason for the order 6215 is because of the way I read in the graph. So this representation is sensitive to the order of the input, but it doesn't matter. The algorithms won't be influenced in any way. It works. Okay, so there's no performance issue dependent on the order in which we look at the nodes. But in the little test example you'll get in the test where I tell you this is the graph and this is the adjacency list, please now execute algorithm XXX by hand. You have to refer back to the adjacency list because that gives the order in which things are. Okay. Does this make sense? Now wait a minute. If 0 is connected to 6, and this is an undirected graph, then 6 is also connected to 0. Do you notice that? If 0 is connected to 6, then 6 is connected to 0. So in a certain sense, we store each edge twice. So we time-space trade-off. We're going to waste a minimal amount of space by storing each edge twice, but that will give us a very quick algorithm to find all the nodes adjacent to the single node. Because if we don't store it twice, I don't know that 6 is adjacent to 0 unless I go through all the edges. Okay? Right. So that is mostly what we'll work with. And I'm not going to look at adjacency sets. You can ignore adjacency sets. That is when we don't allow multiples. Okay? But, so what we get is if I simply store a list of edges, my space clearly is one memory block for each edge. So it's E. To add an edge is immediate. To check whether W is adjacent to V for any V, I have to go through all the edges. Okay. And to iterate through the vertices adjacent to V will take me through all the edges. So if I have a sparse graph, but I know my application gives me a very, very, very sparse graph, I consider this. Adjacency matrix, because I have few edges, it's only dependent on the edges. Adjacency matrix V squared, as we talked about it. Then the one that we will be using throughout the rest of the examples in the chapter is the adjacency list, because that gives me a kind of a balance between the number of edges and the number of nodes. So if it's an average graph, I expect slightly more edges than nodes, but not totally out of whack. So then I have E plus V as my space requirement. Why do I have E plus V? Remember, this is still the notation, right? Actually, if you want to be exact, I need V for my array and then 2E in all the lists. You can go count them. There are 13 nodes in the graph, so I have an array of size 13, and there are exactly 26 little graphies over here. And then to check whether whether a given W is adjacent to V depends on the degree of V. Why? What is the degree of V? It's the number of bits leading V. So to see if W is adjacent to V, I give you a W and I ask, is it adjacent to V? Well, you have to go to V, you have to step through that little increase, that little button. Yes, and that is the size of that is the degree of V. And the same the other way around. If V, and I ask, what are all the vertices adjacent to V? You just step through that little increase, that little button, and there you are. So it depends on the degree of V. Yes.
Could you please explain why it's V for the adjacency matrix and not, because if you have like an array, then it should not be 1 as well. If you get the V and to check if something is adjacent to V, because you've already stored everything else.
Oh, you're talking about this one?
Yeah.
Yes. The difference is, if you give me a W, right? W is 2, and I want to check whether W is adjacent to V. So V is 1, we go directly to V, right, to that cell in the matrix, so therefore it's 1. It's direct access. However, if I give you V, which is 1, so small v, I give you a given node, and I say, please list all the nodes adjacent to V, then I have to go through this whole row to find them, and therefore it's V, the number of nodes. Yeah. Okay, right, so what we're going to do, what I was supposed to do today is to do something called depth first search. I'm not going to try that in 4 minutes. So on Wednesday, we're going to do both depth first search and breadth first search. You have to know that in the test, if you look at previous search tests, I'll give you the adjacency list, and then I say, please write down the nodes as you put them in the depth first search. Please write down the nodes. Alright, I'll see you on Wednesday.
Yes.
I just entered into these ones, so I'll give you more big sheets.
Thanks very much. Yeah.
I have a company. It's one of my ex-colleagues. So Crazy ex. And they got a stunning company. And they are also doing work with Capital Bank. So I sent him off an email and said, if you want to do data science. So I'll put you in contact. Yeah, it's a very nice company.
Very much.
Wag, laat ek gou net hierdie ding toemaak. Anders hoor dit nou